Welcome back once again, everybody. This is Mr. Johnson with Lecture 11, 4.7, Calculating with Chemical Change, aka Stoichiometry. Even if you didn't know this is the moment you've all been waiting for when we can put dimensional analysis, mole conversions, significant figures, balanced chemical equations all together in a single skill, the most important maybe skill in chemistry called stoichiometry. So sit back, relax, and enjoy the ride that's coming your way. I'm going to scroll down toward the bottom of this page here and remind you that a balanced chemical equation indicates the relative amounts of the chemicals involved in a reaction. Those coefficients give us the ratios between the reactants and the products in a chemical equation. For any chemical reaction, the balanced equation may be used to convert moles of reactants to moles of products or vice versa, or to convert from moles of one reactant into moles of another reactant, or moles of a product into moles of another product. The key to these conversions is always the mole ratio, which is determined by the coefficients in the balanced equation. And if we look down here at our mole wheel, and we acknowledge that going from A to B means going from one substance in a chemical reaction to another substance. From a reactant to a reactant, a product to a product, a reactant to a product, whatever it is the mole ratio or the coefficients that do that. You can see I've written that there in my fancy handwriting, that to go from one substance in a chemical reaction to another, A to B, we use the mole ratio or the coefficients. And to remind you that if we're within a wheel, to go from liters to moles, assuming that's a gas at STP, that's where 22.4 comes into play. To go between liters of a solution and moles, that's where molarity comes into play, items to moles, Avogadro's number, and grams to moles or moles to grams, molar mass. So I flipped my page. I'm on page 242 of the ebook, and I apologize, I didn't mention when I started this lecture what page we were on, which was 241 a moment ago. So I'm looking at the sample problem at the top of this page, which says that a student places 7.5 moles of chromium metal in an excess concentrated hydrochloric acid solution. And we're supposed to figure out how many moles of hydrogen gas are formed. So if we look at this balanced equation, we're supposed to remember that the coefficients represent the ratio in which things react or are produced. For every 2 moles of chromium, 6 moles of hydrochloric acid react, producing 2 moles of chromium chloride and 3 moles of hydrogen gas. Again, those aren't the actual numbers of moles that necessarily react or produce. That's just the ratio in which they react or produce, or are produced. So if we focus on what is being referred to in this problem, 7.5 moles of chromium, and we're supposed to figure out how many moles of hydrogen gas are formed. We know that for every 2 moles of chromium that go in, 3 moles of hydrogen come out. So if we look at the bottom here, and we begin by writing moles of chromium, like we normally would in a DA box. You always say we put it over 1, the book doesn't. And then we see this mole ratio that exists between what we're trying to get to, moles of hydrogen gas and moles of chromium, with 3 moles of H2 over 2 moles of chromium, so that moles of chromium cancel. We're left with 11.3 moles of H2 gas, which is 1.5 times 7.5, because the ratio is 3 to 2. So we're seeing the coefficients, or the mole ratio, show up in this problem for the first time, where we are going from moles of one substance in a reaction to moles of something else. That is at the heart of stoichiometry, using the coefficients, or the mole ratio, to again go from one substance to another in a chemical reaction. And that's what we see if we go down the page a little bit, is that conversion from one species to another in a chemical reaction is accomplished using the mole ratio, or the coefficients. So I encourage you to do practice problem 2 on your own, which is going to be going from moles of oxygen gas to moles of water, moles of oxygen gas to moles of water. Pause the video, come back, and see how your solution compares to mine. Hopefully you knew to write a balanced chemical equation first. I neglected to remind you to do that. If water is being decomposed, because it's a binary compound, all it will decompose into are its 2 elements, oxygen and hydrogen, remembering that oxygen is diatomic O2 and so is hydrogen. And when we balance it, we get a 2 in front of water and a 2 in front of H2. And we're focused on the mole ratio that exists between oxygen, the value given to us, and what we're trying to get to, water. It's a 1 to 2 ratio between oxygen and water. So I, rather than rewriting 9.45 times 10 to the minus 5, I just put it over a 1. And then that mole ratio being 2 to 1, put 2 moles of water on top, 1 mole of oxygen on the bottom. That's, of course, so that moles of oxygen cancels. leaving us with moles of water. And when I round to sig figs, I got 1.89 times 10 to the minus 4 moles of water. One substance to the mass of another, because it's fairly common that we will be weighing out things in lab and might start with or end with a mass in reality. Just to look at this mole wheel, this is reminding us that if we start with a mass, the first thing we always have to do is get that value to moles. In fact, that's a crucial step in stoichiometry, is to convert whatever given value you have to moles so that you can take advantage of the coefficients of the mole ratios. So we're going to go from mass to moles using molar mass. For substance A, whatever that is, we'll use the mole ratio or the coefficients to go from substance A to substance B. And then we'll go from moles of substance B to grams using the molar mass once again. We'll do it all using dimensional analysis. So we're going to scroll down, take a look at this sample problem, then I'll give you a chance to practice the problem on your own, and again, compare your solution to mine. So we've got 3.5 grams in this sample problem of silver nitrate being stirred into excess calcium chloride, and we're supposed to figure out how many grams of precipitate are formed. Now, if this weren't solved for us, which of course it is, you'd need to write out this reaction, to write out the formulas of silver nitrate, calcium chloride, to predict the products, write their formulas correctly, and balance it. That's been done for us. Silver nitrate is AgNO3 because their charges are 1 plus and 1 minus. There's calcium chloride. And this is a double replacement reaction, remember? When both compounds are ionic, it's a double replacement reaction. Calcium and silver are switching places, giving us silver chloride and calcium nitrate. And then their formulas on the product side are written based on the charges the ions have, not based on what the subscripts were on the reactant side. So there's our balanced chemical equation. And we in this one are focused on the silver nitrate and the precipitate. And remember, the precipitate is the solid that's formed in a double replacement reaction. So we're going from silver nitrate to silver chloride. Well, if we think back to that mole wheel, the first thing we do is we convert the given mass, in this case silver nitrate, to moles. And that's by using molar mass. Down below, we see the molar mass of silver nitrate put in. So this first step is converting the mass of silver nitrate to moles. Then we always go from moles of given substance, A, to moles of the substance we're trying to get to, B, in this case, silver chloride, and we use the coefficients or the mole ratios between those. It's a 2-to-2 ratio. Mathematically, this step isn't necessary. 2 over 2 is 1. It won't change the answer, but it's important to put that in there regardless, because that's converting in this problem between moles of silver nitrate, what we're given in moles of silver chloride. So please always include that step, even if it's a 1-to-1 ratio. And then the last step is to convert moles of silver chloride to mass using molar mass. And this time you put the molar mass on top so that moles cancels and we're left with grams. So we divide by the molar mass to get moles of silver nitrate, use the mole ratio to get from silver nitrate to silver chloride, and then molar mass again to get to silver chloride. All right, we're going to flip our page, give you a chance to do a practice problem on your own, and then I'll solve it. You can see how. So here's the problem I'd like you to do. We got potassium chlorate decomposing into potassium chloride and oxygen gas. You got 45.65 grams of potassium chlorate that's decomposing. We want to figure out the mass of oxygen gas formed. And it says, think about what you might get for an answer. Remember, the law of conservation of mass says that the mass of everything you start with has to equal the mass of everything you end up with. And because there's two products this time, the mass of oxygen gas should be less than the mass of potassium chlorate because there's going to be some mass certainly left over in potassium chloride. So we should see a mass less than 45.65 for our answer. Take a bit to answer this on your own. Pause the video, come back, and see how you did in a moment. So I took my given mass, 45.65 grams, divided it by its molar mass to convert to moles of KClO3. Then I use my coefficients or mole ratios between given and desired. That's 2 to 3, putting 2 moles of KClO3 on the bottom so it cancels. So now I'm left with moles of oxygen. And lastly, I multiply by its molar mass, 32 grams per mole, to convert from moles of oxygen to grams. And I get, with 4 sig figs, 17 point, ooh, that's not very nice, 17.88 grams of O2. And filming makes me nervous, so I struggled to write well last time. It's 17.88 grams. A little bit better written there is the final answer. All right, I flipped my page. I'm on 245 now, the ebook, looking at this section titled Gases Converting to Volume to Volume. We just did a mass-to-mass problem. Now we're going to do volume to volume. First thing, though, I'd like to tell you or remind you of is that volumes of gases react in the same proportion as moles of gases. Volume and moles are directly proportional. That's not true for mass, because every substance has a different molar mass, and therefore the same number of moles of two different substances will have different masses. But volume and moles are directly proportional. The same number of moles of any two gases, as long as they're at the same temperature and pressure, and they don't even have to be at STP. Again, the volume of the same number of moles of any two gases at the same temperature and pressure will be the same. So if we look at this reaction where one propane molecule reacts with 5 oxygen molecules to produce 3 CO2s and 4 H2Os, or we could scale that up to moles, so too could we say that for every liter, take a look down here at the bottom, for every liter of propane, 5 liters of oxygen react, same ratio, producing 3 liters of CO2 and 4 liters of water. So again, the volume ratio will be the same as the mole ratio. And that can save you some time in a stoichiometry problem. If you're starting with a gas and ending with a gas, you only need to use the mole ratio to convert between the two. You don't have to divide and multiply by 22.4 or another value that you'll learn how to calculate later. So try this quick check down here at the bottom, based on what you just heard, going from liters of propane gas to liters of carbon dioxide by just using the mole ratio, knowing that, again, volume and moles are directly proportional. All right, here we go. So 10 liters of propane will be 30 liters of CO2 because for every liter of C3H8 that goes in, 3 liters of CO2 come out. That's the same as the coefficients, the same as the mole ratio. But remember, mole ratios and volume ratios will always be the same if they're gases, only if they're gases. All right, I flipped the page. I'm now on 246 of the ebook looking at this sample problem. We're going to look at number 2 together, not number 1. 1 was quite a bit like the quick check we just did. It's asking us what mass of nitrogen gas is required to produce 45 liters of ammonia at STP. So we're starting with 45 liters of ammonia at STP, and we're going to mass. This is a volume to mass problem. When we start with a volume, we use, if it's at STP, 22.4 to convert to moles. So we see down at the bottom that the first step, instead of using molar mass, because we're starting with a volume, is to use 22.4. That's converting volume to moles. The next step is going to look just like it did in a mass-mass problem where we use the coefficients or the mole ratio between the substance we're starting with, ammonia, and the substance we're trying to get to, nitrogen. And that's the 1:2 ratio right there. 2 moles of ammonia for every mole of nitrogen. The last step, just like the last problem, because we are converting to mass in the end, is to use the molar mass of nitrogen gas, which we're multiplying by this time, to get from moles to grams. So the difference in this one, as opposed to the last problem we did, was we're starting with a volume, so we have to divide by 22.4 to get to moles, as opposed to last time starting with a mass and needing to divide by the molar mass. Remember, 22.4 only works if it is a gas at STP. If we have a volume of a liquid, we have to use the density or molarity, let's say, to get to moles. So I've flipped my page. I'm on 247 of the ebook, looking at practice problem 3. And I again recommend that you try to solve practice problem 3 on your own, and then come back and take a peek at my solution and see how you did. So consider pausing the video and coming back when you're done. Now this one's a little tricky because we've got to write the equation first, balance it, and then do the stoichiometry. So we've got HCl reacting with excess zinc arsenide. Zinc arsenide's formula is Zn3As2. Zinc I know is a 2+ ion. It is on the ion sheet, but arsenide is not there. Arsenide is not on our ion sheet, but it's in the same column with nitrogen and phosphorus, with the ions nitride and phosphide. They're in column 5, which means they have 5 valence electrons. They all will always gain 3 valence electrons to become an ion. So arsenide is 3- like nitride and phosphide, which is why we get Zn3As2. And that's something you're expected to be able to do, is to use the placement of an element in the periodic table to predict what its charge will be if it's not given to you on an ion sheet. So this is a double replacement reaction. Zinc and hydrogen will switch places, giving us zinc chloride. Zinc is a 2+, chloride's a 1-. So we get ZnCl2, and we were given the formula for hydrogen arsenide, or what's called arsenide, as ASH3. I think if you had written this on your own, knowing hydrogen's the cation and arsenide's the anion, that you probably would have written H3AS with the cation first and the anion second. So had you done that H3AS, that would have been fine, but it's in fact ASH3. So let's take a peek now at the stoichiometry. So I took the volume of ASH3 I started with, divided by 22.4 to get to moles, used the coefficients or mole ratio between ASH3 and HCl to convert to moles of HCl, and then multiplied finally by the molar mass of HCl to get the mass of HCl, which in the end is 85.5 grams of HCl. So we're on our last type of problem here, and this is going to involve problems that have solutions in them, which means we'll use molarity. Remember that if we are given the volume of a solution in liters, the way we convert to moles is through molarity. So we're thinking about this spoke here is going from liters of solution to moles using molarity, as opposed to liters of a gas at STP that uses 22.4. Flipped my page once again, 248 of the ebook, looking at this sample problem, asking us what mass of nickel wire reacts with all the silver nitrate in a 1.25 liter solution of 0.15 molar. So we're given this volume and this molarity. We're going to use the volume and the molarity to figure out moles. And the key here is to write things in such a way to end up with moles. That means you've got to write molarity as it normally is with moles over liters, and then you'll multiply that by the given volume. Volume times molarity is always moles because liters will cancel. So the first step of this, again, is to multiply the volume by the molarity, which converts us to moles. Then we use the mole ratio, as we always do in the next step, to convert from what we're given, silver nitrate, to what we're trying to get to, nickel. And since in this one, once again, we're going to mass, we use the molar mass up top to convert from moles of nickel to grams. Flipped my page, 249 of the ebook, looking at practice problem 2 here on page 249. What volume of a 0.8 molar solution would completely react with 2.4 molecules of chlorine gas? This one's sort of the opposite. We're starting with a substance, in this case molecules of chlorine gas, and we'll use molarity and volume at the end. So a little bit different than the last one, sort of backward. First thing I recommend you do is writing out the balanced equation. Come back and see how you did with that. Then I'll recommend that you finish solving the problem with stoichiometry and come back once again and see how your solution was. So write the balanced equation first, come back, and then we'll solve the problem. Sodium iodide is NaI. Chlorine, because it's diatomic, is Cl2. Forgot to put a G there for gas. This is a single replacement reaction. We've got a compound and an element. And we need to acknowledge the element in this case is a nonmetal. And chlorine, as long as it's higher up on the activity series than iodine, which it is, will replace iodine, the element it's like, the nonmetal, and will form a compound with sodium. So we see sodium chloride over here. Iodine then ends up by itself. Iodine is diatomic. It's a solid at room temperature. If you didn't know that, that's okay, but the S indicates that. And because we've got an aqueous environment, we know that because sodium iodide is a solution, I put AQ next to sodium chloride because I know it's soluble. Sodium is a group 1 metal, and that would render this salt soluble. So there's our balanced chemical equation that we'll now do the stoichiometry on. I just had a moment of weakness. I got so frustrated with my stylus, I might have thrown it onto the ground. Back to the whiteboard. So 2.4 times 10 to the 24 molecules of chlorine, converting it to moles, dividing by Avogadro's number. This takes us from moles of chlorine to moles of sodium iodide. So we're at moles of sodium iodide right now, and we need to get to volume. The molarity is given to us as 0.8 moles per liter, but we can write it as its reciprocal. I can put 0.80 moles of NaI on the bottom and 1 liter on the top, which I need to for moles to cancel and for us to end up with volume or liters, which is the goal. And when I do this, I get 9.96 something something liters of NaI. But with only 2 sig figs, the 6 kicks the 9 up to a 0, which kicks the 9 up to a 1, and I get 10 liters. But remember that trailing 0 is not significant unless there's a decimal somewhere in the number. So I have to put this awkward decimal after the 0 to indicate that it's significant. Or if I want, I can go 1.0 times 10 to the 2 liters. No, 10 to the 1. To give it 2 significant figures as well. So these are both viable ways to express 10 with 2 significant figures. That's it for lecture 11. Mr. Johnson signing out, and go Bulldogs.